Okay, welcome to lesson 7.3, concentration and rate laws. Rate laws and reaction orders. So this is pretty difficult lesson, so pay very close attention. Here is a reaction. NH4 and NO2 are consumed, and we're going to make N2 and 2 moles of H2O. When we're talking about rate laws, we're really only interested in the reactants. We're interested in how fast the reactants are being consumed. So if you look at this data table here, we have the initial concentration of NH4, which is this reactant, and we have the initial concentration of NO2, which is that reactant. It has nothing related to the products. So if we want to determine the relationship between these two, the relationship at which these guys are consumed and these guys are produced, we create something called a rate law. And the only way to determine this rate law is by looking at experimental data. So here is the first set of data. There are 6 experiments, 6 different trials. So the way you read this is up and down, up and down, up and down, up and down. Compare and contrast. So if you look at experiment 1, we start with a concentration of 0.01 for ammonium. And then we go down, it doubles. Like any experiment, we keep the other variables constant. So if we double the ammonium, how does this affect the rate at which it disappears, at which these reactants disappear? And look, as you double NH4, the rate also doubles. So it goes from 5.4 to 10.8, doubled. So that tells us that there's a direct proportional relationship here. If you look here, 0.2 to 0.4, and you keep this guy constant, the rate also doubles, 10.8 to 21.5. Alright, so NH4 has this direct proportionality, okay? It's directly proportional. If you multiply by 2, this multiplies by 2. If you reduce it from 0.02 to 0.01, you reduce it by half, then the rate also halves. So 10.5 halves to 5.4. I think you get the idea. Now let's look at NO2's relationship. The only way we could find the relationship is by keeping this constant. So if you look here, at experiment 4 and experiment 5, you double the NO2, and this is constant. So as you double NO2, here the rate doubles as well. So also with respect to NO2, there's a direct proportional relationship here. So what I just said is stated right here. There is a direct proportionality between NH4 and the rate, and NO2 and the rate as well. Okay, so how do we express a rate law? The rate law is written as rate is equal to some constant. We're going to call it K. Don't get confused with the equilibrium constant. This is not the equilibrium constant. This is different. This is a kinetics related constant. Here we have the concentration of NH4, and NH4 is disappearing, and it's raised to a certain power of m. Okay, we're gonna call this m for now. And then NO2 is also disappearing with a certain proportionality here, and we're going to call that n. M and n, these powers here are not coefficients. So if you look up here, just because there's a 1 there and there's a 1 there, doesn't mean that this is 1 and this is 1. Okay, so don't confuse it with the stuff that we learned from the equilibrium unit. They, instead of m and n, are called rate orders, which I'll explain later. Okay, so in general, you will have this equation, an equation that looks like this, And like I said already, you're gonna set it up in a certain way. So, for example, the rate law is gonna equal rate equals K times A times the concentration of A to the power of little a. I'm sorry, not the power of little a. To the power of m. We don't know what that is because we have to look at data to figure that out. It's not going to be a, okay? Little a. And then you multiply that by the concentration of B, and we're going to set that to n, not little b. And again, we ignore the products. So this is the general setup for a rate law. And these little powers mean something. There are 3 possible ones, okay? And just a few things to consider. The reactants appear in the rate law. The K is a constant and only changes with temperature. M and N are typically whole numbers, not always, but for the purposes of our class, we're going to keep them as whole numbers. If we know the rate law and the reaction rate for a set of reactants, then we could find K. So if we have, for example, if you look at the table above on this data, we know the concentration of reactant A, right? We know the concentration of ammonium. So we could plug this number, for example, here, and this number, we could plug it here, and then we could figure out what little m and little n are, and we know the rate. So the rate is going to be this. And you plug that in, and then we solve for K. So K is a constant. It tells us how fast something is occurring. If K is large, then the reaction is happening very quickly. If K is small, then the reaction is not happening very quickly. It's going by very slow. So again, a lot of this doesn't make much sense to you, but it will once we do examples. So let's look at the first example. Alright, so we're gonna try this problem right here. This is it's a little difficult, it's a little challenging, but I think you guys could do it. So it says here that, again, let me just review everything that I just went over. We could find the relationship between the reactants using something called a rate law. This rate law will tell us the rate at which the substances are disappearing. They don't always disappear evenly. They don't always disappear in the way we expect them to disappear. You guys will see this and later on, and that's why we come up with something called the rate law, where the rate law is going to be defined. Let me set up my pen here. Here we go. Okay, where the rate law is going to be set up in this fashion, where the rate, we write rate is equal to K. This is a constant. K is a constant. It's not the equilibrium reaction constant, okay? So don't confuse this. It's different K. This does have units. It definitely has units. And we multiply this by the reactant concentration. And there's some order to it, some sort of order, which I'll talk about later. And you multiply it by the other reactant, which also has a specific order. The question says find the rate law. Okay, find the rate law. So what we do is we find the relationship among NH4 and the rate. So it's right here. So the way you do this is you have to, because we're trying to find the relationship between NH4 and rate, you have to see where it changes. So here it goes from 0.01 to 0.02. We're doubling NH4. We're looking at experiment 1 and 2. We're comparing those two. Because we're comparing these two, we need to make sure that this right here remains constant, because it's a controlled experiment. So here it doubles, from 1 to 2 it doubles, and from here to here it doubles as well. So what we say is that NH4 shows a direct proportion. a direct proportion where if you multiply by 2, the rate also multiplies by 2. If you look at experiment 1 and 3, we could see that it multiplies by 4, 0.01, 0.04, and here it's constant. So we could use 1 and 3, experiment 1 and 3. So in experiment 1 and 3, NH4 also it's quadrupled, but the rate, if you look here, 5.4 to 2.1.5, is also quadrupled. So anytime there's a direct relationship, 2, 2, 4, 4, half, half, 1/4 to 1/4, anytime it's directly proportional, we call this a first order. Okay, we call that a first order. So M or N will be first order if they're directly proportional. So here we could see that M is directly proportional to the rate. So this little m is going to be a 1. Now NO2, we're going to look at NO2 here. We can't choose 1 and 2, experiment 1 and 2 here, because it's the same. We have to see a change. So we can look at these last 3 here, because we could clearly see a change between experiment 4 and 5. So between experiment 4 and 5, it doubles. And here, the other reactant remains constant. So as we double NO2, the rate also doubles. So again, we start to see this direct proportional relationship even for NO2. So as you double it, so does the rate. Here, from 4 to 6, we could see that it multiplies by 4. And here, it's the same. We want this to be constant. So we could use 4 and 6. And because this multiplies by 4, this also multiplies by 4. So that means it's, if we quadruple it, the rate goes up by 4, a factor of 4 as well. So again, that also shows a first order reaction. So M and N are first power. First order means first power. Just because there's a 1 here and a 1 here doesn't make this 1 and 1. It's just a coincidence that occurred. Now, because the question is asking for the reaction rate, which is this, we can't figure that out because we need to know what K is. K is not given in the equation. We know what NH4 is, which is this. We know what this is because it's 0.1. We could plug it in there. We could plug this in there. We now know M is 1. We now know N is 1. But we have 2 things that are missing, the rate and K. Because K is going to be the same for all of this, we need to solve for K first. So in order to find this, which is what we want, we first need to find this. So the way you do that is we're going to plug in numbers that are already given to us. So for example, I'm going to choose experiment 6 just because it's lower on my screen. You could choose any experiment, any one, and you're still going to get the same K value. So I'm going to choose experiment 6. What I'm going to do is I am going to plug all those numbers for experiment 6 into the rate law. So the rate here for 6 is 43.3 times 10 to the negative 7. Oh, let me write again. That's kind of ugly. So 43.3 times 10 to the negative 7 is equal to K. We want to find that because we can't use these 2 numbers until we find K. And we're going to plug in NH4 here, which is 0.2. And we know this is to the power of 1 because we found the data to have a direct proportional relationship. And NO2 is right there. It's 0.0808, and it's also to the 1 power. Then you're going to divide by 0.2, divide by 0.0808. to get K by itself. And this is 0.2 times 0.0808. Okay, so when you do that in your calculator, you should get, okay, so K is going to equal 2.679 times 10 to the negative 4 power. Now the units are tricky. There are units to this K value. Okay, in equilibrium we didn't have units. For this we do. So this is tricky because every single rate law has a different unit. It just depends what order it is. So this we know is m per second. How do I know that? Because it tells me up here that the rate is m per second. This 0.2, the problem says that it's molarity, and this is also molarity. So look, if you have molarity on top, you cancel it with 1 molarity at the bottom. You're left with seconds, and when you're left with 1 more molarity down here, you guys know that 1 over m at the bottom is equal to m to the negative 1 power. It's algebra. So what I'm going to do, I'm going to rewrite this again here, okay? So K is going to equal 2.679 times 10 to the negative 4 power. It's going to be 1 over m, which is m to the negative 1 power. And the seconds is on top of the denominator. So we're going to leave it as seconds. So this is the units for K. So this is the constant. This is the rate constant. Not the rate law. This is the rate constant, so don't get it confused. This is constant. Rate constant. So anytime it says find the rate constant, this is what they want. But I'm not done yet. I don't want the rate constant. I want the reaction rate of these two numbers that are not in this chart. So now I could use another rate law. So we're going to start another rate law. So rate is equal to the concentration of NH4, forgot my K here, to the first power times the concentration of NO2 to the first power. So now I could find the rate. Rate is equal to K, which is that big number that we just found. 2.68, I'm just going to round it, to the negative 4 inverse molarity per second. Now I'm going to plug in NH4, which is 0.1. And now I'm going to plug in the other molarity, NO2, which is 0.1 here again. This molarity, inverse molarity, cancels with regular molarity. You're left with 1 molarity per second. And it makes sense. Rate is molarity per second. So rate is going to equal this times this times this. And you should get 2.68 times 10 to the negative 6 molarity per second. So that is our rate if we have these two concentrations that are given in the problem. So yeah, that was a very difficult problem. Okay, so if we look a little lower on your notes, just a little recap, a little review. The rate law, we only take into consideration the reactants. It's going to equal some constant. If we are given data and out of nowhere they tell us, hey, here's a certain concentration of NH4 and here's a concentration of NO2, but we don't know the rate because it's not in the table. So you can't find the rate unless you find K. And that's exactly what we did in example 4. We found K, and then we were able to plug in 0.1 and 0.1. And we determined what little m and little n were. We determined that as you double something, the rate also doubled. Or as you quadrupled something, the rate quadrupled. If you halve something, it also halved. Anytime that happens, you're going to put 1. Okay, you're going to put a 1. And again, it's a coincidence that it happens to be the same as the coefficients. The coefficients do not tell us the rate order. So this is the order. The order of NH4 is 1. The order of NO2 is 1. They might ask you for something called the reaction order or the overall rate order. So when they ask for the rate order of just this, for example, NH4, you're going to say it's the first order because it shows a directly proportional relationship. Or for NO2, you're going to say it follows the first order relationship. But when they're talking about the entire reaction rate, we say, okay, we're going to add the order. So 1 plus 1 is 2. So this whole reaction right here follows a second order. So both reactants are first order, but the overall reaction order is a sum of the order. So this reaction is second order as a reaction, not as a reactant, but as a reaction. Okay. Now, what do these orders mean? Now look, we already did the first one. If a reactant doubles and the rate doubles, it's first order. If the rate triples and if the reactant triples and the rate triples, it's first order. But let's say you come through a situation where you double the reactant, but instead of the rate doubling, it actually quadruples. So let's say, what we do is we call this a second order reaction. What second order means is that it increases to the second power. So if you have, if you originally have like the concentration of A is 2, for example, that means that the rate is going to rise by a factor of 2. So it's going to quadruple instead of double. So when that happens, we call that a second order. Second order means you put that change to the second power. But let's say the reactant triples and the rate increases by 9-fold, then we call that a third order. We call that, not a third order, my bad. We call that a second order because, look, 3, if you triple the reactant and it increases by 9-fold, that means the rate increased by 3 to the second power, which is 9. 3 times 3 is 9. So the rate is going to increase by 9-fold. I know that's a little confusing, but it'll make sense a little bit later. Let's say if you increase the rate, let's say you double it, but the rate remains constant, then we call that a zero order. So that's called a 0th order. So this you might want to have on the side when you guys are trying to determine what little m and little n is. So we're actually going to skip this one. So I want you guys to skip example 5 and example 6. Okay. I do want you to know this. So again, if k is large, it's going fast. If k is small, it's going slow. Okay. I want us to do example 7. So again, example 6 and example 5, I want you to get rid of it. We're not going to do those. I want us to focus more on example 7, 8, 7 and 8. Okay. So I'm going to try example 7 and you guys are going to try example 8. So for this question, it says the initial rate of a reaction A plus B makes C was measured for several different concentrations of A and B. The results are as follows. So look, A and B are the only substances we're really interested in. Okay, so we learned already. Let me write this down for you. We learned already that the rate is equal to some constant, which is not found here, times the concentration of the first reactant, which is A, to the power of M, B, to the power of N. We don't know what these orders are yet. That's why we use the experimental data to figure that out. So let's figure out the data for A. Let's find the order for A. So what you do is you look for two experiments where A changes but B stays the same. So for example, here, experiment 2 and 3, it doubles, right? It doubles, 0.1 and 0.2. But here, it's not the same. So we can't use 2 and 3. But if you look at 1 and 3, so I'm going to put it on the side, experiment 1 and 3. If you look at 1 and 3, as you double A, 0.1 and 0.2, what happens to the rate? 4 to 16. It goes up by a factor of 4. So we know that it's not going to be, A is not going to follow a first order. Because if it was first order, it would be 2 and 2. Instead, the rate quadrupled. Okay, so it increased by a factor of 2. So you increased it by 2. So it's 2 times the power of 2, which is 4. So this A is actually undergoing a second order where it's not directly proportional. So this is going to be rate is equal to K times A to the second order. Notice how there's no 2 here in the coefficient, and then you multiply it by B, and we now have to figure out the order for B. So we could use experiment 1 and 2 for B, because look, B here doubles and here it's the same, it's constant. We could use that. So from 1 to 2 it doubles, so B doubles. So as you double B, what happens to the rate? It stays the same. It didn't double, it didn't quadruple, it stayed the same. So that means, according to our rules, that it undergoes a 0 order. So this is going to have a 0. So the question says, or actually you have to look at the questions. So according to the first question, it says, find the rate law, which is this. We just found the rate law. You could write this as your rate law, but you guys know that anything to the 0 power is just 1. So you could also just get rid of this. So the rate law, if it's a multiple choice question, you're going to look for this or this, B to the 0 power. It's the same thing. So any of these two would work for part A. So that's part A. The second question says to find the rate constant. Rate constant is B. I'm sorry, K. I don't know where I got B from. K. So what you do, just like we did in example 2, I believe, you just pick an experiment. So just pick one. I'm going to pick the third experiment, just because it's closer to my screen. So you're going to plug it in. What is the rate? The rate is 16 times 10 to the negative 5 meters per molarity per second is equal to K. A is 0.2 molarity to the second power. So you're going to divide by 0.2 m to the second power. And I'm just going to do this. 0.2 times 0.2 is 0.4 molarity squared. 0.2 times 0.2 is molarity squared, 0.4. This m cancels with one of these m's. And when you divide these two numbers, you get K is equal to 4 times 10 to the negative 4 power. And the units, again, we only cancel one of these m's. So we still have an m down here. So because it's in the denominator, it's actually an inverse. And the second is on the numerator, so it's just seconds. So that's what our K is. Okay, so that's our second answer. That's part B. And then part C says, what is the rate if you have these two values? And again, we don't have those two values on our table. So what we do is we have to find K, which we already did. So this question really walks us through everything we just learned in this lesson. So again, I'm going to write my rate law. Rate is equal to K times A to the second power. Rate, this is what is a rate? That's what we're looking for. K is what we just found, which is 4 times 10 to the negative 4 molarity inverse seconds times A, which is 0.05 to the second power. And if you guys notice, there's a B. This B doesn't matter because it's not part of the rate law, and even if you plugged it in here, 0.1 to the 0 power is just 1. Anything to the 0 power is 1. So we could just ignore this value. This value doesn't make any difference in the rate. And the rate doesn't change. So that's why it's a 0th order, because it doesn't change. It won't change. It doesn't matter. It doesn't matter how much B you throw in the reaction. It's not going to make a difference in the rate. That's what it's saying. So when you solve this, you get 1 times 10 to the negative 6. The units that are left here are molarity squared for this one, right? Molarity squared. That means this cancels with one of these, and you're left with molarity per second, like that. Okay, and that's our answer. So that's the rate for this concentration. Okay, so go ahead and try example 8. If you guys could do example 8, you basically master the whole lesson. And again, this lesson is not easy. I really recommend you watch this podcast twice. Then try as many. Finishing the problem set. Okay, finish the problem set. Finish all the problems that are doable, the ones that we could actually do. From lesson 7.2 to lesson 7.3. I'm going to post the answer key on Google Classroom so you guys could check if you are doing it right. But I think you guys could do it. So you just have to be resilient. You have to not give up. Okay. So let's look at this reaction. So it says that 2 moles of NO react with 2 moles of H2, and it makes this and this. Again, if we're talking about rate laws, we're only interested in the reactants. So the only way we could find the rate law is through experimental data. And again, you guys know the setup. Rate is equal to some constant K times the reactant NO to the M power. It's not going to be 2. Don't assume it's 2. And you multiply that by the other reactant, which is H2, to the, let me rewrite this, it looks really ugly. So rate is equal to K times NO to the M power times the other reactant, which is H2, to the power of N. And again, just review, if you double something and the rate doubles, then that is first order. If you halve something and then the rate halves as well, still first order. It's directly proportional still. If you multiply, if you change the concentration by 100 and the rate increases by 100, then it's still first order. But let's say you double something and then the rate increases by 4. Then that's second order. Or let's say you increase something by 3 and the rate increases by 9. Then it's going to be second order, because 3 to the second power is 9. Or let's say you increase something by 4 and the rate goes up by 16. Then it's second order, because it's 4 to the second power, which is 16 times the rate. So there'll be second order. But let's say you double something and the rate stays the same. Then it's zeroth order. Or you half something and the rate stays the same. Then it's zero order. Or you multiply something, a concentration by 100, and the rate stays the same. It's going to be zero order. Okay? So look. We want to find the order for NO. So we look at NO. You have to choose one where the NO changes, but the other reactant stays the same. So if we look at 2 and 3, again, we can't use 2 and 3. Because here it doubles, but here it also changes. It needs to be the same. So instead we're going to use experiment 1 and 3. So according to experiment 1 and 3, 1, 2, 3, if we double NO, what happens to the rate? It goes from 1.23 to 4.92. It doubles. Does it double? No. It quadruples. Does it quadruple? Yeah, quadruples. So the rate goes up by 4. So we know NO is going to undergo a second order. So this M is going to be second order. So rate is equal to K NO to the second power. Now look at H2. So H2, we could use 1 and 2, experiment 1 and 2. So here it doubles and here stays the same. So as H2 doubles, what happens to the rate? The rate doubles. So for H2, I'm going to write right here. For H2, it doubles. If H2 doubles, the rate doubles. It's directly proportional. So that means H2 is actually first order. So we're going to put a 1 there. So this is the rate law. That is the correct rate law. Okay, so I'm going to rewrite it because it looks a little messy. So we just said rate is equal to NO to the second power. Oops, I forgot my K there. Times H2 to the first power. Let me rewrite it. Equals. I don't know what's wrong with my pen. It's going crazy. To the NO. Stop. H2 to the first power. I don't know why it's going crazy. Pen. Okay. Alright, so that's our rate law. That's the answer to part A. Part B says to find the rate constant. So, rate constant, I'm going to use experiment 3. Use any experiment you want. So, you just plug in numbers and solve for K. So, plug in experimental numbers. So, the rate for experiment 3 is that. It's 4.92 times 10 to the negative 3 power is equal to K, which is what we're trying to find, NO2, which is 0.2, and to the second power, because second order, and then 0.1, because that's H2. And it's the first power, which is just that. Now you solve for k. This is 0.2 squared divided by 0.1, right? You want to get it to the other side. K is going to equal 1.23. You guys know that this is meters per second, and this is meters squared because of the square there, and this is going to be meters again. So this meter cancels with this, this molarity cancels with this molarity, and you have 1 over m squared. So m squared is at the bottom, so it's going to be m to the -2, inverse -2 per second. Seconds on top. So this is k. Now that we have k, now we can find the rate for these two values, which are not in the equation up there. So I'm gonna write it right here. So rate is equal to k, which is 1.23 meter. Molarity, guys, sorry, I keep saying meters. Molarity to the -2 second. And then I'm gonna put, if you look here, K, NO is right here. Plug it in. It's squared, and H2 is 0.15. When you do the math, you get, so when you do this, you get a rate of 4.61 times 10 to the -4. This meter square cancels with the meter square here, and you have a molarity left. And again, I apologize for keep saying meter. It's molarity. Molarity per second. So you should always have molarity per second. You should always have these units for any rate. The only one that has the funky units is the k value. And keep in mind that this is 1.3 meters molarity squared s seconds. You're not squaring this number. It's already it's to the 1 power here. Okay, so don't get confused. Right? So if you could do this, you could do the homework. If you still don't understand it, try looking at re-listening to example 8, example 7, and try listening to example 4, and hopefully it'll make sense. If not, we'll go over some more of these problems on Wednesday. Also, please work on some of these examples from the problem set that you got in class. The only way to really get this is to practice, practice, practice.